Okay, so today we want to talk about which is called the limits. .7 limits. Okay, so we have learned the limits for a sequence, right? So now we want to extend this definition for the limits for a sequence to the limit of a function. Okay, so this is our aim. So before that, let me give you some definitions. So we say that x0 or x0 is called a limit point. Okay, limit point of some set D if there exists some sequence xn. This sequence belongs to D, but not equal to x0. Okay, so this is the minus. Okay, D minus x0. So there exists some sequence in D, but not equal to x0 that converges to x0. Okay, converges to x0. So here is this is the definition for a limit point of a domain D, of our set D. Okay, so if you can find some sequence which is not equal to x0, which is not a constant, okay, x0, which is not a constant sequence, so which is a sequence in D but not equal to x0. And this sequence, if you can find some sequence which converges to this, which converges to the x0, then we see this x0 is the limit point. Okay, so here is the one remark that I didn't say that x0 may not belong to D. Okay, I didn't say this x0 must be in D. Okay, from this definition. If x0 is in D, then you minus. If x0 is outside D, this minus does nothing. Okay, this notation does nothing. It's just the D. So here is the one example. You have a set which is from an interval set, okay, which is from 1 to 3. And then this set, for the set 1 and 3 are not in this interval, right? But 1 and 3 does not belong to this interval 1, 3, but they are the limit points. Of the interval from 1 to 3. They are the limit points. Okay. The reason is you can always find some sequence, right? For example, you can find a sequence which is called 1 plus 1 over n. Right? This sequence is inside this 1, 3, right? And this sequence has a limit which is equal to 1. So this one is a limit point. The same thing for the other one. For example, for 3, you can find 3 minus 1 over n. This sequence is inside this interval, right? But this sequence has the limit, which is 3. 3 is not inside, but 3 is the limit point. Okay, so be careful. What is the limit point? Limit point is you just need to find a sequence in D. Of course, the sequence cannot be the x0, and such that the sequence have the limit which is equal to that number. Then this is called the limit point. Okay, another point, another all real numbers are including the rational number and the irrational numbers are the limit points of the set of rational numbers. Okay. All real numbers are the limit points of the set of rational numbers. Why? Do you know why? Why every point is the limit point of the rational numbers? The reason is, do you remember we have this reason? We have this result. Q is dense in R. Okay, so that means dense means almost everywhere, right? So every point you can always find some sequence in this Q, and such that the sequence is converged to that point, right? So this is called dense. This is the reason, since and because. Okay, so now let's look at how to define the definition for define the limit of a function. If f is a function from D to R, and x0 is a limit point of D, then the limit x approaches x0 of f of x equals L. This is the limit of a function. What does this mean? It means for any sequence xn, which is in D but not equal to x0, for any sequence converging to x0, the sequence of xn, f of xn, converges to L. Okay, so that means the limit at when x approaches x0 of f of x equals L. It means for any sequence converge to any, okay, any sequence converge to x0, then this f of xn, this form a new sequence, this new sequence converge to L. Then we say the limit of the function when x approaches x0, which is equal to L. Okay. So now let's look at some remarks for this definition. First one, if this L exists and is finite, is a finite number, not infinity, okay? Is a finite number, then we say this limit of f of x exists. Okay. 2. Let's look at the it's different, okay? It's different from the definition of the continuity. It's different from the definition of continuity. The continuity says, okay, x0 is inside D, and we have a sequence xn, okay, which approaches every sequence of xn approaches x0, then f of xn will approach f of x0, right? So now what's the difference? It's different from this definition because the first thing, okay, the first thing is we didn't require in this, we do not require this definition does not require this x0 must be in D. We just say this x0 is a limit point of D. This is the one thing. B, f of L, the L in this definition may not be equal to f of x0. So this is the difference. It looks very similarly, right? We have the sequence converge to that number, then the new sequence f of xn will converge to another number. In the continuity, that L must be equal to f of x0. But here, when we talk about the limit of function, we don't require this L must be equal to f of x0, okay? So, 3, if x0 is a limit point of D and also belongs to D, then f is continuous on D is equivalent to say that the limit x approaches x0, f of x is equal to f of x0. So in other words, if the limit point is also in D, then when you find the limit, you can plug in the numbers to find the limit. Okay, the limit equal to the plug in the numbers, right? Plugging x0 inside f, right? Plugging x0 directly to get the limit. If you can do that, then we see this function is continuous. Okay, at D. It's continuous at x0. Okay, so now we want to show some result. Okay, we want to use this definition to show that this limit, this function, a certain function, the limit equals certain numbers. Okay, so the idea is we want to use this way. Okay, we want to use this way. So this is the way we need to find arbitrary. We let xn be arbitrary sequence, and which converge to this x0. Okay, then you try to show this one will converge to L. Then we're done. Okay, now let's look at one example. Let us prove the limit x approaches 1, x squared minus 1 over x minus 1 is equal to 2. Okay, so the limit is already given. Now you need to, we know how to calculate, right? We know how to calculate this kind of limit, but now we want to know why. Okay, why this must be equal to 2. So we use the definition to prove it. Okay, so for this section, the homework, if it asks you to find the limit of certain functions, and you need to use this definition to prove it. Okay. So we use the definition. So the definition says arbitrary for any, right? For any sequence converted to this number. Okay. So now our x0 from this 1, our x0 equals 1, right? So now we let xn, the sequence converge to 1, and xn or xn is not equal to 1 for all n. Okay, so this is an arbitrary sequence, which is not equal to 1, but converged to 1. Okay. Then we consider f of xn, right? Then we consider f of xn. F of xn is equal to this f of x. F of xn, which is just replace x with xn. Right? So this is f of xn. If this is the f of x, if you let this one to be our f of x. Okay. If you let this one to be our f of x, then this would be f of xn. F of xn equal to this one, which is equal to, if you simplify, you factorize the top and divide by the denominator, it would be xn plus 1. Right? This is f of xn. Then we consider this one. So the limit n approaches infinity of this f of x. Then we need to check if this one is equal to, if it's equal to 2, right? So which is the limit n approaches infinity of xn plus 1. So we know the limit of xn, which is given by 1, right? We assume this xn converges to 1. So this limit is equal to 1. So it's 1 plus 1 equal to 2. Right? So therefore, hence the limit x approaches 1 of x squared minus 1, x minus 1 is equal to 2. Very easy proof. Next example, again, we use this definition again, okay, to prove that the limit x approaches 8 of x minus 8 over x 1/3 minus 2 is equal to 12. Proof. Okay, so the first thing is we let f of x equal to this expression, x minus 8, x 1/3 minus 2. We let xn be a sequence converging to 8, and xn is not equal to 8 for all n. Then the limit x, not x, which is n approaches infinity. Now before that, let's equal to 8. Then we consider f of xn, which is equal to xn minus 8 over 1/3 minus 2. Okay, so one thing is you can do that. Let's use another color. You can treat this one because of the denominator. You can treat this one as the xn to the 1/3 power raised to the power 3. Okay, minus 2 to the cube, 2 to the cube, right? So we can use this formula. This is the 1/3 minus 2, and xn. And this one would be 1/3 xn to the 1/3 power minus 2 times. We use this formula for, we use the formula for a cube minus b cube, okay? Which is equal to a minus b times a squared plus ab plus b squared, right? Okay. So here would be x n to the square, so it would be 1/3 plus 2 times x to the xn to the 1/3 plus 4. Okay, so what do we cancel out? You have xn to the 2/3 plus 2 times x sub n 1/3 plus 4. Okay, so now we need to take the limit for this one. Right? We take the limit n approaches infinity of fxn, which is the limit n approaches infinity of xn 2/3 plus 2 times xn 1/3 plus what? Plus 4. So it becomes the limit for the sequence, right? We know the xn has the limit which is equal to 8. So this one would be 8 to the 2/3 plus 2 times 8 to the 2/1/3 plus 4. So this is equal to what? 4. This is equal to 2. 2 is 4. This is 4. So it's equal to 12. Right? So since we have no any limitations or on this this xn, so this xn sequence is an arbitrary sequence, right? Converging to 8. So you have this one, then you by the definition, we say the limit x approaches 8 of x minus 8 over x 1/3 of minus 2 is equal to 10. Right. So you can use this way to prove other problems. So now we can look at some properties. Okay. We will not prove the property because this property we just like we did here using some sequence of xn. Okay. 0.39 or 36. Suppose for f, which is from f and g, which are from D to R, and x0, and for a limit point x0 in D, sorry, not in D, of D. Sorry. Limit point of D. Suppose the limit x approaches x0 of f of x equals a, and the limit x0 of g of x equals b. Then the limit x0, x approaches x0 of f of x plus g of x is equal to a plus b. Okay. So these results you should be very familiar with. F times g would be equal to a times b. 3. Suppose b is not equal to 0 and g of x is not equal to 0 for all x in D, then the limit x approaches x0 of fx over g of x is equal to a over b. Okay, so the proof, I just proved the first one. Okay, very easy proof. Then you can use the same way to prove the other two. The proof of the first one. Okay. So we let f of x, xn, which is a sequence in D but not equal to x0. Okay. Since the limit x approaches x0 is equal to f of x equal to a, that means the limit n approaches infinity of f of xn is equal to a. Right? This is by the definition. For arbitrary sequence converge to x0, so f of xn will be converged to a. Right? Since x approaches x0 of g of x equal to b, then the limit n approaches infinity of g of xn is equal to b. So now let's consider the limit n approaches infinity of f of xn plus g of xn. This is our aim, right? If you can show this limit equal to a plus b, then we're done, right? So it's equal to the limit for two sequences, f of xn plus the limit of g of xn. And we know this one is equal to a and this one is equal to b. So we're done. Right. Okay. So this is the Next part. Now let's look at another theorem. 3.37. Let us consider a function f, which is from D to R, and the function g, which is U to R. Okay. Suppose x0 is a limit point of D, such that this x approaches x0 of f of x would be equal to y0. Okay, certain numbers, would you know that number, the limit is equal to y0. And suppose y0 is a limit point of U. U is the domain of G, such that the limit y approaches y0 of G of y would be equal to L. Okay. We also suppose the image of D minus x0 would be inside the U minus y0. Okay. Then we have the result that the limit x approaches x0 of G composed with f of x, so which is the limit x approaches x0 of G of f of x. They're the same thing, right? Which is equal to L. So this is the limit for the composite function. Okay. Of course, there is a lot of requirements. Okay. So now we want to prove this theorem. So we start from x0. So we have sequence, okay, which is in D but not equal to x0, converge to a number x0. Since the limit x approaches x0 is equal to y0, then we have the limit n approaches infinity of f of xn is equal to y0. Right? This is from the definition. If we let yn is equal to f of x, and we know this yn, because yn x is inside D, right? But not x0, and we have this result. If x is inside D, then it must be, the image must be in U, but not y0, right? Since f D minus x0 is inside U, but not equal to y0, then we have a sequence yn, okay, is inside U, but not 0. And from this definition, from this result, yn has a limit y0, right? And yn converge, sorry, here's braces, converges to y0. Okay, so we have a sequence converged to y0 in the domain U, right? And since G has this result, right? Since g, the limit, and y approaches y0 of g of y is equal to L, then we have the limit n approaches infinity of of g of yn, right? A sequence is equal to L. This is by the definition again, right? You have a sequence converged to this number, then this limit means the sequence has the limit which is equal to L. This is definition. Okay, so now let's replace back. Therefore, the limit n approaches infinity of g yn is equal to, we let yn to be f of xn. We just replace back. Is equal to L, right? In other words, what does this mean? This is the limit n approaches infinity of g composed with f of xn, right? This means this one, which is equal to L. And we know this xn is arbitrary sequence, right? Which will converge to x0. So, since xn is arbitrary, then we have the limit x approaches x0 of g composed with f of x, which is equal to L. Okay. So we finished the proof. I didn't use any technique, right? Any trick play. I just repeat the definition again and again, right? Use the conditions we have in the problem and just repeat the definition again and again, right? Limit becomes the limit. Limit of function becomes the limit of a sequence, right? Then we use the limit of sequence to prove, since this sequence is arbitrary, right? So we use the limit of sequence to go back to prove the limit of function. Okay, you can read this proof carefully. I didn't use any technique, right? You see, I just used the information we have, then we use the definition to explain what we have, right? Then we combine together to get your result. Okay, so there is a very interesting problem. So suppose we have the limit x approaches 0 of f of x minus f of 0 over x is equal to L. This is we know. Okay. Then if we let our g of x is equal to this f of x minus f of, if we let this one. So in other words, the limit x approaches 0 of g of x would be equal to 0, or equal to L. Right, this is what we have. So what about this one? The limit x approaches 0 of g of x to the kth power. This is the composite function, right? The outside function is g. G has the limit equals to L, right? The inside function is x to the n, x to the kth power. If x to the kth power, x approaches 0, which would be 0, right? So it satisfies the conditions we have in here for this composite function, right? G, when x approaches 0, equals some number, okay, L. Then this one approaches this one equal to, inside it, this is 0 again, okay? This y0 is 0, right? No, yeah, it's 0. It's 0, and this is 0, so here it must be 0, right? So we have the inside function have the limit which is equal to 0. Then you can put together, it would be have the same value. So that means this one is equal to, you can treat this one as a composite function, okay? And it's equal to L. So what does this mean? This tells you something that f of xk power minus f of 0 over xk's power will converge to L. If you know this one, then you can find the limit for this one. The same thing for here. C times k, C times x. So which is the limit n approaches infinity, or, oh, sorry, not n. X approaches 0. So cx, when x approaches 0, would be 0, right? So which is this 0, right? So this is g of x, so which becomes what? Becomes f of cx minus f of 0 over cx would be equal to what? Would be equal to L. Okay. So if you want to find not cx, let's look at this one. What is the limit and x approaches 0 of f of cx minus f of 0 over x? Okay, so it's not a g of cx anymore. This one is not equal to g of cx, right? But we can change it. This is the c times x, f of c times x. All right, what's the limit for this part? This part is L, so it's equal to c times L. Right. So this is an example to tell you we can use the composite function to find the limit quickly sometimes. Okay, so this would be the topics for today's lecture, okay, which is about the limit of functions. So next time we will start our last chapter in this course, okay, which is about the differentiation derivatives, okay. Which is about chapter 4. We have 5 sections, but the last section is kind of just notation of the Leibniz notation, and then we need to do some derivatives, mean value theorem, Cauchy mean value theorem, and other results. Okay, so we stop here. Any questions? Okay. 36. Okay, is this one? 36. Oh, 36.